Now let's construct the algorithm to give us the LU factorization of a matrix. Now last time we did talk about how these two matrices are obtained, and the matrix L, well, the matrix U is the matrix from the Gaussian elimination. You know, when you apply Gaussian elimination to a matrix, you will get an upper triangular matrix. That's directly from the Gaussian elimination method. The lower triangular matrix will come from those multipliers from the Gaussian elimination method. The lower triangular matrix has 1s in the diagonal, and the lower part of the matrix are made of those coefficients. We can easily construct the algorithm from the Gaussian elimination method. So here we're going to change, instead of x equals, right? When we call Gaussian elimination, we're actually solving a system of equations, and then the function g will return the vector x, which is a solution of the system. But we want to write an algorithm to give us the factorization of the matrix A. So we are not solving any system yet. So we don't need the right-hand side B. We only need the matrix A. So we want to factorize the matrix A. So let's call this as LU fact. Now instead of returning the vector x, we want the function to return the two matrices L and U. So I'll do L, comma U. So this is telling Octave that this function will need to give us back two matrices, matrix L and the matrix U. Okay, in the program we're gonna get rid of this everything that deals with the right hand side B, so we don't need this part here, and we don't need the backward substitution because we're not solving the system. We're simply when you solve the system, you need the right hand side. We're not solving any system here. We're just factorizing matrix A. All right. So the matrix U, the upper triangular matrix, comes directly from the elimination here. So where you see A here, we're going to put U here, U there. And U originally needs to start just like A. U needs to be A at the beginning. And then we do the elimination on U. And that gives us, at this point, this will simply give us the upper triangular matrix. Now, the lower triangular matrix is made of a diagonal matrix made of 1s, and then the multiplier is being put here at the bottom of this matrix. Now, in Octave, there is a very simple command to create these diagonal matrices. It's called EYE. So if I do, for example, I4, that gives us the diagonal matrix. It's actually the identity matrix, right, with 1s in the diagonal here. So if I do I6, and it's a diagonal matrix, 6 by 6 matrix with 1s in the diagonal. So here we can start the matrix L as a diagonal matrix, I and then N. Okay. And now we need to put those multipliers in the matrix L. We can do it right here, right after we find each multiplier. So where do we put these multipliers? Well, remember that J, right, in the algorithm, J goes from 1, 2, 3, right, up to 3 here. And then the I's go from J plus 1 to here. So the J's are the columns and the I's are the rows. So I and then J is the column. And that will be those multipliers, each multiplier. Okay, I'm going to erase that. And that's pretty much it. So this will give us the matrix L and the matrix U. So when you save this, be careful when you save. You want to save as LU fact. .n. I already had one file with that name. So here is LU fact A. Let's test. I want to test with the example that we had before. Here. So here's the matrix 2, 3, 4, 8, 42. Now, I'm not sure if the LU matrices will be the same as these two here. I'm not sure if I got these two matrices from the Gauss elimination. Again, remember that a factorization of a matrix A is not unique. You could have many different L's and U's like that. So let's test. Here's a matrix A, 2, 3, 8, 42. Now let's call the algorithm. So I call L, U equals to LU fact, and then I provide the matrix A. Here they are. So here's the lower triangular matrix, here's the upper triangular matrix. Notice that it's not the same, so it'll almost look the same, but it's different. 2, 3, 0, 5, and here's 2, 3, 0, 30. Well, let's test. Let's multiply L times U and see if we get our matrix A back. Yes, here it is. 2, 3, 8, 42. See, that's the matrix A. So it works.